Swayam Prabha. Digital India. Educated India.
We shall continue with the example that we have been discussing last time. Meanwhile, I could get useful information which is a data source for Indian locations. That is a HTTP address is given over here. I shall write it down in case you cannot go to this original document. Hyphen scc.pdf. So, this has got one of the examples that you can see clearly on the screen. Mean monthly global solar radiation on a horizontal surface in megajoules per meter square a day for selected locations of India. I have shown here with something to bring in. These numbers you cannot read, but you can always go to the original source and have a look at the data that is compiled by Solar Energy Center, MNRE, Indian Meteorological Department. So, this has got lots of contents which you can have a can you focus on the screen? Yeah, the sun, solar radiation spectrum and the various measuring instruments and the locations where the measurements have been made and the terminology, and this is about 23 locations that we have got, which basically has got mean hourly ambient temperature and for each month, then the monthly global solar radiation and the monthly diffuse radiation, and given I have given here selected from Srinagar, which is more or less a high latitude location in India, up to Trivandrum, which is in down south Kerala, which is almost low latitude, which I have shown the latitudes here. Srinagar has a latitude of 34 degrees 05 minutes north, and of course, the corresponding longitudes also are given over here, and whereas Trivandrum has 8 degrees 28 minutes N. One of the ideas is not just I have taken south, north, east, west and something middle, so that you will have a feel for the variation in the solar radiation. If you look at Trivandrum, this is the diffuse radiation, this is the global radiation. The average is 19.45 megajoules per meter square day, which is the annual average, and it varies only between 17.38, which is the minimum I could see, and goes up to 23.4 megajoules per meter square day. That is, if you statistically say that the standard deviation is very low, and as you are going very near the equator, the variation between January to December or summer June to December is very small, and like that you can make an interesting observation for the remaining locations, and that was my idea of showing it here. The corresponding diffuse solar radiation on horizontal surface is given. One of the ideas of giving this data particularly to you is that you might verify the H d bar by H bar correlations for the Indian locations, because these correlations were developed with mostly North American data. So, their applicability has been tested, but now you have got a lot more data for the Indian locations. So, you might as well re-establish or validate those correlations. So, these numbers may be useful to us when we solve some examples for the Indian locations. Yeah, this was the example based upon F chart method and phi bar F chart method we have been discussing. It is at a location of latitude 40 degrees N, a process heating system employing flat plate collectors facing south with a slope of 40 degrees, area 50 meter square has been installed. The collector parameters are FRUL is 2.63 watts per meter square degree C, and FR tau alpha normal. This we have done, but this is for the sake of your continuity, 0.72, and it is supposed to T minimum is 60 degrees C and 12 kilowatt for 12 hours a day. Of course, the other data ground reflectance is 0.2 for the month of January. H bar is 8.6 megajoules per meter square day, and ambient temperature is -5 degrees C. So, this is the given data which we wanted to calculate what is the critical radiation level. This, after a lot of preliminary calculations, we have calculated for example, mean declination for the month of January is -20.9 degrees, and then the sunset hour angle is 71.3 degrees. In this case, omega s dash also will be 71.3 degrees, and we got the extraterrestrial horizontal monthly average daily radiation to be 14.4 megajoules per meter square day, and then the clearness index KT bar is 0.6, that is 8.6 upon 14.4, and the diffuse fraction HD bar by H bar we got as 0.3 using Collatz-Pereira-Raval's correlation. Then we got RB bar 2.32, I remember, and R bar 1.91. Right, all these calculations we have done in detail, and from this we proceeded to calculate RTN, which is 0.178. Once again, this is a correlation due to Collatz-Pereira-Raval, and RDN is 0.164. This is a relation due to Lewin Jordan, and remember that this is I at the noon time by H for the day or the monthly average day. This is ID by HD. In other words, if we know HD or H, we can calculate I or ID. Then in calculating RN, we need hd by h, that turned out to be 0.41, and similarly ultimately we got Rn equal to 1.59. So, R bar upon Rn is 1.91 by 1.59, which is about 1.20. I can't. R bar by Rn is equal to 1.91 by 1.59. So, subsequently we estimated the critical radiation level, which turned out to be 0.909 megajoules per meter square. This is for an hour. Okay. This is where I wanted to continue from here. So, this I c equal to 2.63 times 60 minus 5 times 3600 upon 0.72 into 0.94. This 0.72 is Fr tau alpha normal, but my IC formula I need is Fr tau alpha bar, which is Fr tau alpha n multiplied by tau alpha bar by tau alpha n. So, this is equal, this tau alpha bar by tau alpha normal is equal to 0.94. I shall show the calculations for this, so that we will have an exercise in calculating tau alpha bar also. So, if you look at it this way, the absorbed radiation S bar can you come here? Okay, okay, okay. Sorry, then okay, fine, bye. अच्छा AC बंद है या नहीं सर, नहीं बाबू को गर्म लग रहा है, नहीं सर AC चल रहा है सर, मुझे तो ठंडा लग रहा है सर, पता नहीं, ठीक है, सोचा ये क्लास 4:30 के बाद बंद करेगा? नहीं ना,
वो तो सारा दिन रात चलता है।
ठीक है, ओके। सो ये एडिट कर दीजिए। So the absorbed radiation S bar is given by H bar R bar times tau alpha bar. So this should be equal to the beam component H B bar R B bar tau alpha bar B plus the diffuse component D times 1 plus cos beta by 2 plus H bar into ground reflectivity into tau alpha for the ground reflected radiation times 1 minus cos beta by 2. So what we want is tau alpha bar by tau alpha n. So I can divide throughout with this. That should be equal to, if I write H B bar as H bar minus H D bar by H bar times R B bar upon R bar times tau alpha bar B by tau alpha n plus H D bar upon H bar times tau alpha bar D 1 plus cos beta by 2 plus rho g tau alpha bar g by tau alpha n into 1 minus cos beta by 2 times 1 upon R bar, here also 1 upon R bar. This we have done, but then I wanted to say that the number 0.94 simply written, you should not wonder how you got it, how we got it. So this is and how do we calculate? Tau alpha bar B upon tau alpha n is the effective transmittance absorptance product for the direct radiation, for which we need theta b bar. That is the effective angle of incidence for the direct radiation, for which we have already demonstrated that there are charts. So from the charts I have picked up, for phi is equal to 40 degrees, beta is equal to 40 degrees, month of January, and gamma is equal to 0, theta b bar is equal to 41 degrees. This is approximate because I had it from the charts, and the effective angle of incidence for the ground reflected radiation theta g is from the Brandmühl and Beckmann correlation 90 minus 0.5788. All these relations are there in your earlier lectures. So you should not be looking surprised where from these things have come. So this will turn out to be 73.148. Now you see we got a theta g greater than 60 degrees, calling for some relation for theta to be valid other than the Astor relation, which is valid for less than 60 degrees. Similarly, theta d for the diffuse radiation is 59.68 minus 0.1388 beta plus 0.001497 beta square. This will turn out to be 56.52 degrees. So this is within that Asher limit of 60 degrees. So what we get now is each one of them. So tau alpha bar B by tau alpha n which will turn out to be in the relation 1 plus b 0 into 1 by cos theta minus 1. So, I made the calculations. The data is not given whether it is a 1 glass cover or a 2 glass cover collector. We will see what difference also it makes. If it is 2 glass covers, 1 minus 0.17 by 1 by cos 41 minus 1, which is 0.94475 for 2 glass covers. And if it is a single glass cover, I use the constant incidence angle modifier coefficient B 0 as 0.11 minus upon 1 upon cos 41 minus 1. This turns out to be 0.96. This is for 1 glass cover. If you recall the tau alpha variation with theta, 1 glass cover will be a cover up above the 2 glass covers curve. Then similarly, tau alpha bar diffuse by tau alpha normal also in the less than 60 degrees zone. So, I will have 1 minus 0.17 into 1 upon cos 56.62 minus 1, which is 0.86183 for 2 glass covers, and this will be 1 minus 0.11 into 1 upon cos 56.62 minus 1, which is about 0.91 again for 1 glass cover. So, for the ground reflected portion, so tau alpha g, tau alpha n, I will use the relation proposed at IIT Kharagpur 2 times 1 plus b 0 into cos theta. This is nothing but at theta is equal to pi by 2, this will be 0, and at theta is equal to 60, it coincides with the previous relationship. So, if you do this and you have point, this is 2 into 1 minus 0.17 into cos 73.148. So much of accuracy is not needed, because there are many approximations we have been doing. This comes out to be 0.48, and if it is, this is for 2 glass covers, and if it is 1 glass cover, you have got 2 into 1 minus 0.11 into cos 73.148, which is 0.516 for 1 glass cover. Okay. So, just let us write it down. Tau alpha bar b upon tau alpha n, this is 1 glass cover, this is 2 glass covers, which will be 0.96 and 0.94475. Tau alpha bar d by tau alpha n for 1 glass cover 0.91 and for 2 glass covers 0.86183, I think. Yeah. And the last one, of course, is tau alpha, next one, tau alpha bar g by tau alpha n for 1 glass cover, it is 0.48, for 2 glass covers it is 0.516. So, if I plug it in the relation that we have written, tau alpha bar by tau alpha n is equal to 1 minus h d bar by h bar into r b by r bar, r b bar by r bar 1.91 times 0.94475 for two glass covers plus 0.3, that is h d bar by h bar into 1 plus cos beta by 2 times 0.86183 by r bar 1.91. The third component will be rho g times 1 minus cos 40 by 2 into tau alpha bar ground effect is 0.48 by 1.91. If you do this, you will get 0.9282, and if you replace all these numbers, this is for two glass covers. So, this is about 0.93, which is given as 0.94. That small difference may be due to the theta b bar, but if I do with one glass cover, tau alpha bar by tau alpha n is 0.9485. What I have done is I have replaced this 9447 with 96 and this one with 0.91 and this one with 0.516. Okay? So, it will be enhanced. So, the truth may be between 9.5 and 9.3, the average is 0.94. So, since we do not have that data, but remember we now got the detail of calculating the transmittance absorbance product or the absorbed radiation for a day. So, as I was mentioning or emphasizing, this 1 plus b 0 into 1 by cos theta minus 1, the incidence angle modifier coefficient relation for tau alpha by tau alpha n in general, depending upon the theta that you use for the direct radiation or the diffuse radiation or the ground reflected radiation, it will give you the appropriate tau alpha by tau alpha normal. So, we got this. Now, the other thing was what is the non-dimensional critical level, that is x c bar is I c by your I t noon equal to, which we have already calculated as 0.909 by R T n 178 times R n into 8.6. So, this is also in megajoules and now this is also in megajoules. So, there is no problem. This non-dimensional critical level will be 0.37. Okay? We got the non-dimensional critical level, we got the critical level. Then second problem, I am separating it out. What is the maximum utilizability? That is, we want V bar max. That is from Klein's correlation exponential to the power a plus b R n by R bar times x c bar plus c x c bar square, and the constants a 2.943 minus 9.271 kT bar plus 4.031 kT bar square, which will come out to be minus 1.17. B will be 4.345 plus 8.853 kT bar minus 3.602 kT bar squared equal to minus 0.33. Of course, it is time taking, and but yet I am preferring to write these relations as many times as possible, because when you solve in the examination or when you want to solve the problems, the relations will be at different places in a textbook, or if you compile all of them, there are subtle differences like ID by I, HD by H, HD bar by H bar, H0 bar. So, there are minor differences, but then a repetition of these things may give you an idea that okay, if we are calculating the monthly average daily utilizability, the constants A, B, C are there, which are different from the constants A and B in the Collier-Raoults correlation. And you should also have some sort of an idea that these things are related and correlated to clearness index for some reason, whereas A and B in Collier-Pereira and Raoults correlation for RT are just geometric factors. So, if you remember the little bit of physical basis behind these correlations, you will not pick up the wrong relation. So, this is 306. I will have a little reprieve if I do not continuously talk. This is 0.704. So, phi bar max, we got it. Of course, you can plug in these numbers as 0.51. Okay. So, once again, first thing is all preliminary R, R bar, Rn, H0 bar, KT bar, HD bar by H bar, IC and IT noon. Then from that the critical radiation level we have calculated, then the non-dimensional critical level, then the maximum utilizability corresponding to T minimum, based on which we have calculated IC. So, that is the sequence. Third part, solar load fraction met by the system. So, we need the variables y, which is AC, FR, tau alpha bar, HT bar, n number of days in the month, by the load. The load in this case will be 12 kilowatts, that means 12,000 watts for 12 hours multiplied by seconds multiplied by 31. Actually, this comes out to be 16.1 gigajoules. If you divide this by 10 to the power 9, you will have 16.1 gigajoules. So, y will be, area is 50, FR tau alpha normal is 0.72 multiplied by tau alpha bar by tau alpha normal 0.94, just now we have calculated, times R bar 1.91 times 8.6 into 10 to the power 6 joules multiplied by 31 by this chunk 12,000 into 12 into 3600 into 31, which will come to 1.07. Remember, y is of the order of 1, 2, 3, whereas x dash will be little larger. Okay. So, phi bar max y, which in a way represents the maximum possible solar load fraction that the system can meet, will be 0.51 times 1.07 equal to 0.55. In other words, if anybody calculates and comes out with a number larger than this, obviously there is a calculation mistake. And the second variable x dashed is area multiplied by FR UL times just a scaling factor 100 multiplied by the number of days or number of seconds in the month by the chunk 12,000, 12, 3600 times 31. Please remember, when the load is given in joules or megajoules, make the consistent units. If it is kilowatts for certain time, you have to convert it to joules. Okay. That is, power is done over a period of time, which makes it the energy. This will come out to be 2.19. Storage is the standard storage, which is 350 kilojoules per degree C. This directly does not come into calculation except in the RS, which is the ratio of standard storage to the actual storage and in this case it is equal to unity. So, now solar load fraction F by the phi bar F chart correlation is phi bar max y minus 0.015 times e to the power 3.85 f minus 1 times 1 minus e to the power minus 0.15 x dash times r s to the power 0.76. So, this I will try to put all the number that we know, so that it will be easy to iterate later on, because this is an implicit relation. 0.55 minus 0.015 times this is not known, because f is not known, 3.85 f remains as it is, times 1 minus e to the power minus 0.15 into x dashed, which is 2.19 into 1. So, this is 0.55 minus 0.042 e to the power 3.85 f minus 1. So, what I have done is I have set myself up a table, calculate LHS and then the RHS. Okay. So, I know phi bar max y is about the maximum solar load fraction, if you forget all this losses part. Okay. This is basically a loss, and this implicit relation indirectly expresses f again in terms of f. So, this f I know should be less than 0.55. I assume it to be 0.52. RHS will come out to be 0.523. Oh, good. Good agreement. I tried with 0.53. I got 0.5218. So, it may be 5.2 or 5.3, and if you want to see the efficacy, you may start with 0.4, then this will be too large, then you have to bring it down. So, it is not as difficult as it looks like when you have this long equation. It is only just if you have the calculator, particularly if you have a programmable calculator. Even if you have no idea, except that it will be nice if you have the idea that f will be less than this phi bar max y, and particularly f should be less than 1, then the iteration is not a difficult thing. It does not take more than 5 minutes. Now, this is the solar load fraction we have calculated as per the specifications of the system, meets 12 kilowatts 12 hours a day for the month, and collector parameters are given for 1 month January. Then you can calculate that F January to F December, and then capital F will be sigma Fi Li upon sigma Li. I do not have the number, I will let you know tomorrow if you want, but the whole thing is repetitive, and it is certainly not very easy for hand calculation for all the 12 months. So, a small program can be written for this, and you can make 12 calculations with the power of the computers available now, practically quite fast. 4. Solar load fraction we will try to calculate. If tank losses are included, right, and given the area overall loss coefficient product of the tank is 5.9 watts per degree C, and environment or the surrounding temperature we will call it T dashed is at 20 degrees C. So, T minimum we know is 60 degrees C. So, I will assume as a first guess for the tank temperature to be 62. Okay. So, first guess. So, roughly that is T minimum plus 2 degrees C. So, with this assumed temperature of the tank, losses from the tank Q T will be equal to 5.9, that is UA product, times 62 minus 20 times 3600 joules, 24 times 31 number of days, so many joules. This comes to 0.7 gigajoules. So, it is not too small. So, now the system is supposed to meet the load inclusive of the tank loss. So, load on the system inclusive of tank losses which will be 16.1 gigajoules plus 0.7, that comes to 16.8 gigajoules. Now, my phi bar max y is proportional to this original 5.1 times original y 1.07 into 16.1 by 16.8, which is 0.53 phi bar max y in not subscript. Okay. Similarly, x dashed should be enhanced equal to 2.19 into 16.1 by 16.8. This is equal to 2.10. So, again f is phi bar max y minus 0.015 times e to the power 3.85 f minus 1 times 1 minus e to the power minus 1.5 x dashed into r s to the power 0.76. So, you write it f is now 0.53 minus 0.015 e to the power 3.85 f minus 1 into 1 minus e to the power minus 0.15, sorry, this should be minus 0.15 times x dashed is 2.10 times r s to the power 0.76. So, I set up myself the same table. Now, I will come out by iterative process. F T L equal to 0.51. Now, you remember this is the solar load fraction, rather I will just call it the load fraction including tank loss. Okay. That is our notation. So, this we said as an iterative process. To set up the iterative process, average utilizability, not the maximum, because this is sort of a overall load fraction met by the solar energy system, which does not distinguish between the load on the system as needed by the consumer as well as the load because of the additional tank losses to be met by the system. So, utilizability corresponding to this average utilizability, which we just call it phi bar, is that 0.51 by 1.03 F T L by y. That is right, y is 1.03. Yeah. So, this will be equal to 0.49. So, again I just wanted to make sure, note how we got this number 1.03. 1.03 is the original 1.07 into 16.1 by 16.8, original y multiplied by enhancement or depreciation factor because of the tank loss. Okay. Now, this phi bar will turn out to be, again we have got the you use A, same constants equal to minus 1.17 and this is 0.49 already known to us, equal to e to the power A plus B r n by r bar. Just be cautious, because everywhere else it is r bar by r n written. I do not know in the textbooks, and including I picked up the same habit, but the relation is in terms of r n by r bar, x c bar plus c x c bar square, where A is minus 1.17 and B is minus 0.33 and C is 0.704. So, r bar by r n, again you see r bar by r n 1.2. So, if I plug it in, everything is known to me. So, x c bar I back calculate, which will turn out to be 0.37. So, this is an equation set up to calculate x c bar. So, this is caused by a certain temperature difference. So, I will not go about the roundabout way. X c bar straightforward equal to 0.37 equal to 2.63 into that suggested average inlet temperature minus T A times time unit F r tau alpha normal into point tau alpha bar by tau alpha n this is whole thing is IC by IT noon RTN Rn times 8.6 into 10 to the power 6 to make it joules. So, my Ti bar minus Ta equal to 68.5 degrees. So, Ti bar is 68.5. Remember, T is a minus 5. So, it becomes plus 5 over here, minus 5 is 63.5 degrees. So, suggested or so average (63.5) plus 60. This is the minimum. This is a possible value, comes to 61.7, close to the guess 1 equal to 62. If you are not satisfied, you could start with 61.7 and due to the calculation, you may come out with 61.8. Okay. So, that is the FTL we got, and F, the solar load fraction, will be FTL times 1 plus QT by L minus QT by L, that formula we have got, which will be equal to 0.51 into 1 plus 0.7 by 16.1 minus 0.7 by 16.1, which will be equal to 0.49. Remember, here this is the original load on the system. Okay. This is the original load on the system. Because we defined FTL as a QS plus Q tank by L plus Q tank. Okay. So, that we divided throughout with L, the load on the system. So, in this formula it is important to remember this is 16.1, not the 16.8, which included the tank losses. So, F again is we got 0.49, which essentially means F reduced from 0.53 to 0.49, about 0.04 in 0.5, that is approximately 8% reduction. So, tank losses will reduce the solar load fraction by about 8%, but that can significantly depend upon the minimum temperature at which energy delivery is needed. In the case of F chart, it is a single unit. So, the correlation takes care of the losses, etc. In the case of V bar F chart, if it is 60, if you have got 80, it would have been much higher number than 8%. Okay. So, this, as we have said right from the beginning, the once again to repeat and to make you understand the logic behind it, we estimate the tank loss assuming a tank temperature. We treat the tank loss as a part of the load, recalculate the coordinates, variables x dash and y, and use it in the phi bar F chart method to find out the load fraction. That load fraction is the so called load fraction inclusive of the tank losses. Whether the guess temperature is correct or not is found out by obtaining what we call the average utilizability, which corresponds to some sort of an average Xc bar, which should have been corresponding to a average inlet temperature to the collector. So, the suggested possibilities being T minimum equal to 60 or whatever, and this Ti bar, we take the average, and if this average is close to the guess that we made in the beginning, then we will stop the iteration. Otherwise, you take the new value that is obtained and go through the procedure again. So, this is how the tank losses can be taken care of. Next time we shall find out the effect of the heat exchanger and then the effect of the heat exchanger plus tank losses. Okay? Until then, bye.